x minus y is x plus minus y, and x over y is x times y inverse A, define y inverse separation. We also have a notion of order, and organize the rationals into the positive rationals, the negative rationals, and zero. So he is doing building up the number system with algebraic, and now this absolute value and comes to the part of analysis. We also have organized the negative rationals. In short, we have shown that the rationals give form an ordered field. So he is writing these sort of words, they are redundant. No, you don't know what is the meaning of an ordered field. So that's why I am always saying he is writing the book for the people who know some. Yeah, that's he's writing for them. One can now use these basic operations to construct more operations. There are many such operations we can construct, but we shall just introduce the particularly useful ones: absolute value and exponentiation. To me, what is very important is absolute value. Absolute value exists. If x is a rational number, the absolute value of you write absolute value that way. In two vertical lines, you write the number. If x is positive, we did this part, didn't we?
Yeah.
I remember we did this. And I said you need to grow. I remember very well non-degeneracy of distance, it will never be negative. The symmetry dxy, we discussed this. Epsilon closeness, we came to that also. That means the distance, actual distance. Let epsilon greater than 0 be a rational number and let xy be rational numbers. We say that y is epsilon close to x if and only if we have dxy less than or equal to epsilon. This definition is not standard in mathematics. Many things he do are not standard in mathematics, but almost all the exercises are very standard. You need to do all of them. I went through actually all of them. The definition is not, we will use it as scaffolding to construct the more important notions of limits and Cauchy sequences later on. And once we have those more advanced notions, we will discard the notion of epsilon close. Did I jump? No.
No, you need to go down.
Then example 4.36, I mean, we don't need to spend time there. Let xy, z, w be rational numbers. If x equals to y, then exists epsilon close to y for every epsilon greater than 0. And conversely, if x is epsilon close to y for every epsilon greater than 0, then we have x equals y. So that is a real analysis stage part. I mean, it's not anything big, but that has, this proof is very analysis. Let's prove only that because it is of analysis stage at least. So we are going to prove first one, no? If x equals y, then x is close to y for x, epsilon close to y for every epsilon greater than 0. No need to prove actually. Conversely, suppose if x is epsilon close to y, so we need to prove if x is epsilon close to y. It has a hyphen, no, after epsilon is close to y for every epsilon greater than 0, then we have x equals to r. This idea you use in every theorem in analysis. Every theorem. If something is epsilon close to y for every epsilon greater than 0, we have x equals r. In any theorem you prove in analysis, not in algebraic flavor, analysis flavor, it is everywhere, though it is very simple proof. So, what should be the first line I should write to them? No, only by looking at this. We want to prove this thing. Okay, say this is a proposition. What I am asking is, what should I write first? Then you are writing a letter, for instance, you first write date, then address, then to whom the letter is written, then his address, then says Jayaveva, no, something like that. You write, I don't know. Then something like that, and you begin the letter. It is like that if you are proving this.
Let x and y be an arbitrary rational numbers.
No, as you here, I mean, it is given of let x, y, z, w be rational numbers. So that part is given. So if something is written let or suppose, then you don't need to say it again. It is already given in the proof. Now here, this thing is not if x is close to y for. Now, what I am trying to say is here, you don't need to say that x is rational anymore. It is something given. You don't need to say so. Assuming that, now in the proof, what shall I write? It's not a big thing, but the reason I started to prove, as I told you, in real analysis or complex analysis, even in functional analysis, every proof use this idea. Every proof. It is very elementary, but we need to learn how to write. Anyway, so what should be the first line in my proof? We are going to prove this line. Putava?
Suppose epsilon is larger than 0 and x is close to epsilon close to y.
Yeah, something like that. Putava, what will you write?
Let epsilon greater than 0 be arbitrary.
Let epsilon greater than 0 be arbitrary. You need to learn to write a proof. It's very important. That's the reason I am here. Because assuming that I will teach you the atlas one, you said atlas one is one, this is atlas. Okay. Let epsilon greater than 0. You can quit here, but if you want, you can write be arbitrary also. It is redundant because if you say let epsilon greater than 0, then it is understood that it is arbitrary. But to make sure we write like that also. That is the first thing. Then what can you say, Buddha?
Suppose x is epsilon close to y.
Suppose, very good. Suppose x is epsilon close to y. Then what does that mean? He is using dxy or absolute value. I myself cannot tell you. Thus, dxy, no? Less than epsilon. No? If you write like this, how can I prove x equals y? We couldn't prove. All of them are correct. So what do you say? How to prove this?
We know that dxy is always greater than or equal to 0.
Yeah.
Since
By the way, before we prove this thing, do you believe it? Because this is not very big mathematics now. What you are saying is you have to give numbers x and y. Somebody is saying distance between x and y are as close as you please. As close, that's what it's saying. X is epsilon plus y for every epsilon means x and y are as close as you think, as close as you desire. If say dxy, maybe it is less than or equal to 0.10 million zeros and 1, 0.10 zeros and 1, anything. Then, do you believe that x must be equal to y? Yes, Uttara? Okay, then, how do we prove this? Whenever you are writing a proof, if you don't understand, you may know the mathematics part, but if you don't understand how to write, you have to ask me. Not how to solve the problem, but writing part, if you don't understand real convincing way, you should ask me right away. So what do you say?
Because I said 0 is dxy is greater than or equal to 0, and there's another inequality mark over there, strong induction concept comes to mind, but I don't understand it properly.
Regardless of what we do, there is no way we can prove x equals y. I mean, whatever, if you go through the book, you don't get the theorem or proposition or corollary or something x equals y. Nothing will. So, only way to do is that proof by contradiction. That's the only way. All these are very good. All these are very good. I mean, I gathered that you learned something, but it's still not there. Of course, the 1 or 2 months, you may not get the rhythm. So, we are going to prove this thing by contradiction. So let's prove without saying let me say right precise. Let us prove this by contradiction. What I am trying to do is you have to be very sure that we are proving it. It is not like when you are in before O-level, teacher comes and do geometry problems. Teacher writes something, and teacher proves it. Okay, we proved it. You don't know what it is not like that. So, if you want to prove this by contradiction, you need to assume. So, prove this by assume x is not equal to y. If x is not equal to y, then dxy is strictly greater than 0. Right? Then dxy is strictly greater than 0. Now, we want to say if we want to assume question says if x is epsilon close to y for every epsilon greater than 0. Now we have this much. Now I wrote here, let's prove this by contradiction. I don't know, I have to change it. Of course, you can prove it by contradiction also, but then your statements must be accompanied with, go together with what you are saying. Did you try to bring some milk toffees or something?
No.
They said you were on the way to some place to buy some chocolate or milk toffees in the morning because it is a rainy day. Okay, assume x is not equal to y, then dxy greater than 0. Thus, how shall we write? Well, now, you see, this is a very small thing, but writing a proof, it must be terribly rigorous, even though it is a small thing to be proved. Let us prove this by contradiction. I wrote 2 or 3 statements earlier, then I erased them. Now assume x is not equal to y, then dxy greater than 0. Then this is some positive number. Choose or let, whatever the word you like. Let epsilon equals, let me put epsilon 0, equals dxy. Then epsilon 0 greater than 0. I have now positive number epsilon 0. Now, what should I say? I am not talking about a very big thing. I am talking about how to write the proof. But proof must be really convincing to you. Now, all the things are, so far, what is on the board is very clear. No? Assume x is not equal to y. Then dxy greater than 0, obvious. Let epsilon is equal to 0 dxy. Then epsilon 0 greater than 0. Right? Then what, Kuta? You can say, no, what is that? dxy, if you want, you can say, what is that? It is not the case that dxy is less than epsilon 0. Oh, well, yes, I can write like that. However, less than or equal, no, so let me say epsilon is equal to this thing divided by 2. To make sure. Epsilon close is less than this way, no? Less than or equal, no? When you say epsilon close, it means dxy less than or equal to epsilon, no? Not strictly less than. Notice that it is not the case that dxy less than or equal to epsilon 0. By dxy is not then less than or equal to dxy divided by 2. So I assume x is not equal to y. I have proved this is incorrect. There is an epsilon 0 greater than 0 such that x is not epsilon close to y. That is, x is not epsilon 0 close to I. So I have, are you with me?
Yeah.
What happened? You have to understand, because I mean you just began 1 or 2 months ago, not 2 months even, it's still less than 2 months. You are used to doing mechanical manipulations. Here this is logical writing, so you need to get used to it. It may take some time. I assume this is not true. I have proved that this is not true either. Then still let's prove this by contradiction. Oh, do I have to change this word contradiction? What I have shown is, if this is false, then this is also false.
That's it. Contraposition.
Contraposition. Contraposition. This is a very simple thing. I am not talking any big maths, but writing part. If x is close to y, epsilon close to y for every epsilon, then we have x equals y. Let's prove this by contraposition. I guess it is one word only in this book. Sometimes it is 2 words in some books. I don't know. I myself write sometimes as 2 words and sometimes as a single word. Assume x is not equal to y, then dxy greater than 0. Let epsilon 0 is equal to this number, dxy divided by 2, then epsilon 0 greater than 0. Notice that it is not the case that dxy less than or equal to epsilon 0. It is not true. That means I have proved there exists an epsilon greater than 0 such that x is not epsilon close to y. So I have assumed this is not true. I have proved that this is also not true. This completes the proof by contraposition. This completes the proof by contraposition. Because in this process you are learning 2 things. You have to make sure that you are learning his construction of natural numbers, integers, rationals and real numbers. But in the meantime we are learning how to write proofs, how to prove it. Are you convinced that I have proved it? Are you? Because you have to say yes, that you said yes, oh actually you said no.
I got that.
You got that. Because certain things that you are learning are mechanical. For instance, let's go to next one. Let epsilon greater than 0. If x is epsilon close to y, then y is epsilon close to x. Nothing like here. If x is epsilon close to y, he says dxy less than or equal to epsilon. Therefore, dyx is also same thing. So, no arguments. Now, let's go to the next one. Let epsilon delta greater than 0 both. If x is epsilon close to y and y is delta close to x, then x and z are epsilon plus delta close. Again, nothing mathematical. I mean, of course the elements. First one says dxy less than or equal to epsilon. Then next one says dy z less than or equal to delta. Then you know dx z is less than or equal to dxy plus dy z. No? Triangle inequality. We discussed that? No? Yes? I think so. So it is no big deal. All of them are mechanical. Many things we learn are mechanical. I mean, this kind of things are in analysis, what we do. Are you sure of that or not? All of them are mechanical. Now, even part E, let epsilon greater than 0, if x and y are epsilon close, that is dxy is less than or equal to epsilon, he writes dxy, I cannot remember, mod of x minus y. Which one does he write? Same thing. Dxy. Because, I am reading and sometimes forget. If x and y are epsilon close, they are epsilon dash close for every epsilon dash greater than epsilon. Again obvious, no? Yes or no? When I say obvious, don't agree with me because I said. If suppose x and y are epsilon close, that means dxy less than epsilon. Now let epsilon greater than 0 be such that epsilon dash greater than epsilon. Therefore dxy less than epsilon dash. So nothing like here, this. They are mechanical. Many things are like that. Even let's see, let epsilon greater than 0, I am talking about g. If x and y are epsilon close and z is non-zero, then x z and y z are epsilon times, we call it that what? Mod descent or? Absolute value is it true? Because I always say mod. Again, that is also obvious. This is the only analysis part in this theory. Whole A, B, C, D, E, F, G. I mean, proving G is obvious. Let epsilon greater than 0. We write suppose x and y are epsilon close and z is non-zero. If z is non-zero, absolute z is also non-zero. Therefore, x z, y z, the dx z, y z means absolute value of x z minus y z. Then absolute value of z times x minus y. That is absolute value of x minus y times absolute value of z. Absolute value of x minus y less than epsilon. Therefore, that quantity is less than epsilon times mod z. Clear? Oh? Clear? Very clear? So, many things are mechanical. Then this one the same way. But you have been doing all the homework, no?
Yeah, I submitted this.
Is he grading careful?
He hasn't graded analysis homework. I don't know why.
He hasn't graded it?
Yeah, he has appointed the teaching assistant to grade them.
Yeah.
But still nobody has graded us.
So you are not improving. I will talk to him tonight. You must be given comments about your proofs. For this sort of thing, you have to get to the rhythm of mathematical, analytical proofs. Not the single homework set was graded.
The analysis one, no, not it.
Oh. But he told me he will grade.
Yeah. Don't know maybe he's busy or something. He told us he appointed the teaching assistant to grade homework.
Too bad. I have to ask him because sir. Now, can you write the proof for B, C, D, E, F, G, H? However, if you have a question like this and if you are not sure of your logic, you have to ask me. Now, asking me how to solve B, C, D, E, F, G, H doesn't make any sense. They are different things. Okay. Anyway, these are natural ones. We only prove the most difficult one, H. Okay, thank you. Exercise 4.3.2, which is absolute value, thus. Let me remember. One should compare statements A to C of this proposition with reflexive, symmetric and transitive axioms of equality. It is often useful to think that, anyways, now I am worried about, because there are other things where your logicalness is important in your homework. Some of them. So, I mean, you haven't got it yet. So, let's see what to do. Maybe he could not find somebody. At the very beginning, he told me he will grade. I was wondering whether he could grade, because I don't know, I mean, how, because logical and it's not that he doesn't know, but it is a different ball game. One should compare statements A to C of this proposition with reflexive, symmetric and transitive of equality. It is often useful to think of the notion epsilon clause. It's an approximate substitute for that of equality in analysis. Now he goes to exponentiation. That is a mechanical thing. That's mechanical thing. He says, let x be a rational number. To raise x to the power 0, we define x to the 0 is equal to 1, he says. In particular, we define 0 to the 0 equals 1, something we don't like, no? Anyway, so he does that sort of thing. Now suppose inductively that x to the n has been defined for some natural number n. Then we define x to the n plus 1 equals x to the n times x. Even that this writing I don't like actually, because he says now suppose inductively that x to the n has been defined for some natural number n. I mean, actually we have defined x to the 0 equals 1. You don't have to suppose. Can you see what I am saying? He has defined x to the 0 equals 1. So he has defined x to the n for some natural number n.
That's the same.
Now he is saying, now suppose inductively that x to the n has been defined for some natural number n.
That n could be 0 and
N could be 0. That's not good. The way it should be written is that let n be a natural number for which x to the n is defined. That's the correct way of writing. You see what I am saying? Because you have defined x to the 0 equals 1. Then 0 is a natural number, so you have defined x to the n for some natural number n. Then now you are saying, now suppose inductive. No, that's not good writing. Because what I am saying, not good writing means then your brain won't get logical, no? But see my point? Now what you say is, let n be a natural number for which x to the n is defined. Then x to the n plus 1 is. That's the way to write. Because this is a place where in maths many people don't understand many things because brain is not logical. Okay. So, I mean, these proofs may be the mechanical ones. Properties of exponentiation. Let xy be rational numbers and let them be natural numbers. We have x to the n times x to the n, which you can prove them, no? I don't think they are difficult. When I say not difficult, what I mean is they are mechanical. That's what I mean. Somehow your homework must be graded. He told me, I don't know, he told me he will grade at the very beginning. Then for certain things he said he will take a tutor. I don't know. Then modulus, no last one? Part D, modulus of x to the n is modulus x raised to the power n. I guess I'm just clicking and going. Do you understand or I'm just clicking?
And this is
So, anyway, so here what he did, regardless of what is written, how he defines x to the n, we define x this is an inductive definition. He defines x to the 0. Then he takes any integer n for which x to the n is defined. Then he says x to the n plus 1 is x to the n times x. So we know the meaning of x to the n times x. As a result, x to the n is defined for each n. Why? Because x to the 0 is defined. X to the 0 is defined. Now, let n be an integer. Integer or what?
I forgot natural.
Natural. N be a natural number. For which x to the n is defined. Then x to the n plus 1 he defines as x to the n times x. So by this step, since x0 is defined, when you put 0 here, x to the 0 plus 1, you get x to the 0 times x. So x to the 1 is x. Then now x to the 1 is defined. Now if you put 1 here, 1 plus 1 is x to the 1 times x. X to the 2 is defined. Similarly, x to the 3 is defined. X to the 4 is defined. Can you see what I say? X to the 5 is defined. It is going for any n. So these are inductive definitions. Now he is saying we now define the exponentiation of negative integer exponents. Exponentiation to a negative number, let x be a non-zero rational number. Then for any integer, for natural numbers, he defined x to the n even if x is 0. But for the for the negative exponents, he is taking a non-zero rational number. Then for any negative integer, negative n, we define x to the minus n is 1 over x to the n. Got it? Thus, for instance, x to the minus 3 is 1 over x to the 3. X to the 3, from this definition, you know, x times x times x. So, this way you can define for any n. No problem. Let xy be non-zero rational numbers and let n be integers. Then we have x to the n times x to the m. I guess before we proved that if n and m are natural numbers, we proved this thing. Now he is also prove it for any n m integers. They can be negative, 0 or positive, whatever. Do it when you are writing a proof for them, they are mechanical proofs. So you all must be able to do it. I mean, there is no big deal there. Anyway, you have submitted all the homework to this day. Have you? I don't know. Now I have to check with him. Homework must be graded. That's how you learn. No? That is how you are. Without doing homework, you cannot learn. I mean, homework should be graded and commented very carefully. At the very beginning, he told me that he will grade. Sometimes he has told me that he will hire a teaching assistant. So, I will call him right away. That's not good. But what you are saying is you have done all the homework, no? Yes. So part A, x to the n times x to the n is x to the n plus m. So I don't know whether you need to consider cases where both n and m are natural, both n and m are zero, both n and m are negative, and one is negative, positive. I don't know because I myself haven't written a proof. But you have to write a very clear proof, even though it is not analysis type, it is algebra, but it must be very clear. Again, x to the n raised to the power m is x to the nm, as well as xy to the n is x to the ny to the n. I'm not going to. If you have, however, trouble, even though they are manipulating proofs, you have some trouble, you can ask me. But what I'm saying is, you must be able to do this kind of things. You must be. However, they should be graded. Very bad, no? If x greater than or equal to y strictly greater than 0, then x to the n greater than or equal to y to the n greater than 0 if n is positive, and other way goes other way around if n is negative. So it has some mathematics because if then statement. No? So if you are proving the second one, what should I write to the first? I am asking you. If you are going to prove the part B, it says if xy, what we know is let xy be non-zero rational numbers. That's what we know. Now the proof, we will go on to prove if x greater than or equal to y is strictly greater than 0, then x to the n greater than or equal to y to the n. Let's forget about how to write the proof. I should spend some time for. I didn't think of spending time with you for mechanical things. And you must be able to do that. It's very bad now that somehow. Homework is not graded. I don't have time actually to grade. Because the thing is that, I'm busy, I'm actually these days writing some books, very busy, and I have spent so much of time with this person. So many hours. So what do we, let's look at this thing. Let x, y, because this one has only x and y, I will let x, y be, oh that's all. Yeah. X, y be non-zero rationals. Non-zero rationals. Then we need to prove if proposition, let me write. If x greater than or equal to y greater than 0, then this part only, x to the n greater than or equal to y to the n greater than or equal to 0, is greater than 0, if n is positive. If n is positive. I am not asking how to prove this thing. Before you write the proof, you should know what to write. It's a different thing that you write. I say, suppose this thing, then do this thing. That is mathematical writing, no. Your younger brother who doesn't know anything about this, he asks you how to do this thing. How do you do? You have x greater than or equal to y greater than 0. He doesn't know any Terence Tao. He says, I want to prove if n is a positive. So you say n is positive. I am not asking a proof type discourse, but I am asking you, what would you tell your brother? I want to prove x to the n greater than or equal to y to the n. How do you prove?
So x to the power of n means that x is multiplied n times.
Yes.
So because x is greater than y, so multiplying x by itself for n times must be greater than y multiplying by itself.
That's what we need to do. Must be but. My question has nothing to do with this course now. You go home, you have a younger brother or sister, ask, hey, you have seen if x greater than or equal to y and y greater than 0, and if n is supposed to be integer, you have shown that x to the n greater than or equal to y to the n. He says what you asked, the same thing. It must be, x n times greater than or equal to y n times. It must be. So you cannot tell him the same thing, Mali, you are right, as you said, it must be. You cannot say like that. So this is O-level type proof, not I am asking now, O-level type. In our case, we have to write, suppose x greater than or equal to y and then we supposed to be integer, blah blah blah. We do bunch of things.
Can you do a substitution for x? Can you say x equals y plus z? Let z be a positive number.
Of course, you can do that, but then your brother will hit you. That is true. Can you move this thing for a second? If you are going to prove something like part B, then you have to know actually how to prove it in A-level manner. Then you write in our style the proof. Because there may be sometimes gaps in the A-level manner proof, but that's what which convinces us about the proof. So, if xy greater than 0 and non-zero, x to the n equals y to the n, then x is equal to y. For some of them, there are things that you need to think. There are things. They are maths that you are aware of to this day, not you are learning from this class. Now, proving this x to the n greater than or equal to y to the n method is, I haven't taught and you are not learning here. But this logical thing, you are learning here. Okay, we have, okay, let's go. How about part B, for instance? How should we prove this thing? This is obvious. Mod of x to the n is mod x, absolute value, absolute value, yes. Absolute value of x to the n is absolute value of x to the absolute value of x to the n is absolute value of x raised to the power n. For n equals 1, this is true. So you say, let n be a let n be integer. So first, then you should say your proof for n equals 0, no? N equals 0, x to the 0 is 1, x and y are non-zero, no? Then mod x raised to the power 0 is also 1, therefore it is true for 0. Again, similarly, therefore it is true for 1. Now you say, let's go for natural numbers, positive integers. So you say let n be a natural number such that absolute value of x to the n is equal to mod x to the n. Now you want to prove absolute value of x to the n plus 1 is mod x raised to the power n plus 1. That is easy, no? Absolute value of x to the n plus 1 is absolute value of x to the n times absolute value of x. Absolute value of x to the n is here absolute value of x raised to the power n. Then you get the result, right? You get the result. if you must be an expert in A-level type of thing, and there is no question here. Then part C can be sometimes challenging, no? In some way. Xy greater than 0, n is non-zero, x to the n equals y to the n. Then x is equal to y. How will we be proving this thing? Because this is obvious. Obvious means we know that it is true. That's what I mean by obvious. Anything comes to your mind? How to do? Maybe you
Controversy.
I think you have to go by controversy. If x is not y, not equal to y, then xn is not equal to y to the n. I guess you need to go like that. So, anyway, certain things, though they are manipulative, it needs some thoughts and of course some time. Anyway, now what is the most important thing here? We have proved the absolute value of x, which is x itself if x is positive, and it is 0, if x is 0, it is of course 0, and if n is negative, negative x. So you notice something, absolute value of x is always non-negative. Absolute value of x is always non-negative, that is the thing. So I noticed that certain manipulative things are also difficult, no? Prove that 2 to the n greater than or equal to n for all positive integers n in Hughes induction. Let's look at that for a second. I'm sort of doing things that I didn't plan to do. How do you prove this thing?
Induction.
Okay, it says induction. 2 to the n greater than or equal to n. Okay, so if you put for n equals 0, according to him, for all positive integers, 2 to the 1 greater than or equal to 1 is true. Suppose 2 to the n greater than or equal to n. Then 2 to the n plus 1, you multiply both sides by 2. No? Then you have, if you multiply by 2, left hand side is 2 to the n plus 1. Right side is 2n.
It is greater than or equal to.
N is greater than or equal to 1. That side has now 2n. 2n is like n plus n. 1n is greater than or equal to 1. So you can say n plus n is greater than or equal to n plus 1. So that's true. Okay. Gaps in rational numbers. I guess I spent time. But anyway, I came to know many things today. Especially that your homework is not graded. How can you learn without homework getting graded? That's very bad. You didn't ask him, sir, where is our graded homework? You didn't ask.
No.
No, it is very important. Anyway, gaps in the rational numbers, he says. Anyway, doesn't matter because we have to go through. But very important, if you have a logical type of difficulty in the proof, you should ask me. Logical type of difficulty now. Proving this sort of thing is not a logical thing. It is, I guess you couldn't do because I'm just asking like, boom, boom, boom. Maybe you cannot reply. But these are the things you can do. Anyway, gaps in the rational numbers, he says, because if you draw a real line, if you put rational numbers, there are so many gaps without rational numbers. That's what he is talking about here. Imagine that we arrange the rationals on a line, by the way. Arranging x to the right of y if x greater than y. That's usual, we call number line, no? We call number. Here he is talking about number line. This is an unrigorous argument since we have not yet defined the concept of a line. But this discussion is only intended to motivate the more rigorous propositions below. Inside the rationals, we have the integers. Integers are also rationals, that's what they are saying, which are thus also arranged on the line. Now we work out how the rationals are arranged with respect to the integers. Gaps in the rationals. This is a very important exercise. Interspersing of integers by rationals. Let x be a rational number, then there is an integer n such that n less than or equal to x and strictly less than n plus 1. In fact, this integer is unique. You know this is true. No? If you take any rational number, there is an integer less than or equal to that rational number. Any rational number is in between two consecutive integers. No? Left hand side can be equal, right hand side then cannot be equal for sure. That is for each x there is only one n which is like this. In particular there is a natural number capital N such that n greater than x. I don't know why. Natural number n greater than x. So here for instance, if x is 0 or negative, if x is negative, it doesn't say anything. But if x is a positive real number, if you take a positive real number, always there is a natural number n greater than that positive number. That's a very important result in analysis. We use it a lot. And you studied the Archimedean property, no? Did you? Not yet? Ah. That is, there is no such thing as a rational number which is larger than all the natural numbers. What it says is you cannot find the natural number greater than all the rationals. I mean, consequence of this. So this is what does it says about the normal? Did he prove? Exercise. So this is a very important homework. Very, very important one. 4.1 result. This is true not only for any rational numbers, for any real number. If you are given a real number x, you can find an integer n such that n less than or equal to x, and of course x is strictly less than n plus 1 probability. I mean, what this says is, if you take, say, like, you take x, when you take a number x is either here, no matter which x you choose, it can be here or it can be here. This is n plus 1. Any real number must be like that. I mean, if real number is this side 1, then our n is, then this is my n, which is going to be n plus 1. He cannot include less than or equal. Over there also, he is not including. This is a very standard and important result. The integer n for which n less than or equal to x is strictly less than n plus 1 is sometimes referred to as the integer part of x. I have seen A-level people say like that, and is sometimes denoted by, they have some word for that. Pali. You know this thing? No. Integer part of it, he writes, for instance, so 2.5 is equal, this is equal to 2. Integer part of this number is 2. So this is like that, almost square brackets, but not at the top. That kind of thing. Anyway, important homework. important homework. I will call him tonight, right away. You learn not, you have to do the homework, but somebody must grade it so that you should learn whether you have done the mistake, because it is possible. Here what is a interspersing rationals by rationals. If x and y are two rationals, such that x less than y, then there is a third rational is in such that x less than z less than y. That is easy. Because if you take any two rationals x and y, x plus y is also a rational. No? X plus y divided by 2 is also a rational. So if x less than y, then the middle point is x plus y by 2. So this proposition is easy. Right? This is an easy one. Despite the rationals having this dispenses property, they are still incomplete. There are still an infinite number of gaps or holes between the rationals. Real numbers are not all rationals. No, I mean there are real numbers which are not rationals. That's what the next one is. Although this denseness property does ensure that these holes are in some sense infinitely small. For instance, we will now show that the rational numbers do not contain any square root of 2. He is saying there is no real number x for which x squared is equal to 2. He has written a proof here. Again, he has made it so difficult. I don't know why. I always like to write easy proofs. So that way, student learn better. Because you can read this proof. So, I don't know whether you can read it because I guess it is too difficult. Not be too difficult. This style is kind of tough. But the usual proof is there are two proofs. One is let me write one. Other one we can write. When you do this, I told you this one important homework before all. Using that we can write another proof. Suppose there is a rational number let's see what he wrote P cube, no? Yes. Number P over Q such that this, I am not writing precisely, but idea. P squared over Q squared equal to 2. P over Q whole thing squared is 2. I am on the way to prove that, not this proof, but he is writing this to kind of to read first. P over P. I am taking P and Q have no factors. Where P, Q have no common. In that sense, it is called reduced. I cannot remember even common factors. Now, from here you get P squared is equal to 2Q squared. I want to get a contradiction, no? Here I am choosing P and Q so that they don't have any common factors. What is the English word for that? Then two numbers reduced form. I cannot read. You notice that I have forgotten English also. No? Because for years I did not do anything. When you cancel all of them, reduce form or what? No, you haven't been to. You studied in Sinhala medium. Everybody studied in Sinhala medium, no? It doesn't matter. P squared is equal to Q squared. I am saying, regardless of the fact that we don't know the English word for that, I am choosing P and Q so that no common factors. Now P squared is equal to 2Q squared. Now P squared is divisible by 2. No? Because P squared is equal to 2 times Q squared. No, thus 2 divides divides. In other words, P squared is even. No? Thus 2 divides P squared. In other words, P squared is even number. Now I want to say P is even. P and Q are integers. No, I did not write all of that. I'm just going to give you the idea only. P is either even or odd, one of them. If P is odd, suppose P is odd by any chance, then it is like 2m plus 1. Then P squared is 4m squared plus 4m plus 1. This is 2 times 2m squared plus 2m plus 1. If P is odd, then P squared is also odd. Therefore, here P must be even. Thus, P is even, that is 2 divides P. Proof is very short. I am assuming there are rational numbers. There is a rational number PQ. The P and Q are integers, such that P over Q squared is equal to 2. Where PQ have no common factors, then P squared is equal to 2 squared, plus 2 divides P squared. Then P is even, therefore 2 divides P. So P is equal to 2k for some k. Belongs to n, no? An integer. For some, without writing this way, because now n has different for some positive integer k. Integer, maybe I am not writing the right word, integer, natural number, etc. P, somehow P must be an even integer. Therefore, P squared is 4k squared is equal to 2q squared. So, q squared is equal to 2k squared. Right? We proved if P squared is equal to 2q squared, then P is even. Now here I am saying I have got q squared equals to 2 squared, therefore q is even. Now both P and Q are even. Now they have a common factor. I started assuming that they have no common factor, contradiction. That is the standard proof of there is no rational number like this whose square is 2. You understand පුතා? මේකම තවත් විදිහකට ලස්සනට ලියන්න පුළුවන් මේ අර ගාන හැදුවෙන් පස්සේ. මේක හරියට you understand this well, no? Yes? So his proof is kind of very long. I guess he is up to something else. Time is 11 o'clock. Because we should read a little bit about his proof, maybe then after tea.